We are solving now paper 6. It is paper 6 variant 2, May-June 2024. Time allowed is 1 hour, alternative to practical, and of course this is 20% of the curve you can say on the syllabus. Let's start. 40 marks, 1 hour is the time. So a student measures this. Question number 1 talks about a student measures the spring constant K. Measures the spring constant K of a spring by two different methods. By the spring constant, by Hooke's law, we can find F is equal to Kx. K is the spring constant, and K will be equal to F over X. If there is a set of data given, we can find the value numerically, or even if the graph is plotted of force against extension, we can take the gradient of the graph to find the value of K. Many ways are there. The spring constant K of a spring is the measure of how difficult the spring is to stretch. So if it requires greater force to stretch it by 1 millimeter, its value of K is more. And if it requires less force to stretch it by 1 millimeter, it means its value of K is less. That is the meaning of this sentence. Now method 1, it looks to be conventional method. It will approach towards the graph. Method 1, A. The student attaches the spring to the clamp as shown in figure. As shown in figure 1.1. So spring is there and 500 grams mass is attached. Suspends a mass 500 grams from the spring, pulls the mass down a small distance and releases it. What will happen? As a result of this release, my dear friends, what will happen? The spring will be oscillating up and down. So in this case, there will be vertical oscillations. So the mass oscillates up and down. The student measures the time small t for 20 oscillations, which is n. Number of oscillations. It can be number of cycles. It can be number of vibrations of the mass. The reading on the stopwatch is shown in figure, and check it is in minutes 0, seconds 17, then 17.76 seconds, actually to the 100th of a second. Now mass 50. The period P of the oscillations is the time for one oscillation. Calculate the period T of the oscillation. Record your answer in table 1.1. T. How much was the T? It was 17.76, if I'm not wrong. That was shown 17.76 in period. And if you remember, even very first chapter of our syllabus, period is equal to small t divided by n. And right now small t is 17.76 divided by n, which is number of oscillations, and it is n is equal to how much? 20. So n is equal to 20. So as we will calculate it, so answer will be 17.76 divided by 20, and we are getting 0.888. So 3 decimal places it is there. 3 decimal places are there. So we can write 0.89. That I think will work, no problem at all. If we are using what? 0.89. So I can write here 0.89 and seconds are already given there. Suggest how the procedure can be improved to increase the accuracy of the result. And how many marks are there? Only 1 mark is there. So we can do it many ways. Measure time t for greater number of oscillations. greater number of, before you did for 20, you can make now for 25, 30, 35, up to 50 workable, no problem, but it will be time consuming at the same time. Anybody having any problem at any moment, feel free, you can ask me. Now K1, calculate the value K1 for the spring constant of the spring. Use the equation K1 is equal to 19.7 over T square. So 19.7 over 0.888, but be very careful, square. See, the time was here 0.89 I used, but you can use the exact value 0.888. Yes, Lajade.
Mister, to improve the accuracy, can't we just also repeat the experiment and find the mean?
No. You know why so? Maybe repeat also it means so that you are measuring the time for one oscillation and then you are repeating for one oscillation 10 times. Very difficult because every time the percentage uncertainty will be high. Only one oscillation. Measure the time for greater number of oscillations in this case. Like you did it for one oscillation. Reaction time error. Reaction time, you did not start the stopwatch on time when you start counting the oscillation. Then you did not stop also on time, on exact time. So what will happen? Like 1 second is the period. Like here 0.88 second, and reaction time error is 0.2%. It means 25% you are doing wrong. But if you have taken 10 oscillations, so that 25 divided by 10, it will become only 2.5%. Further 10, it will be 1.25 and so on. So more number of oscillations will improve the result and decrease the percentage uncertainty. To understand it in a more simple way, you started a business, you got a loss of 1 million reals, you are alone, so the all loss is on you. But if there are 10 partners, it is a company, Shirka, 10 partners, so 1 million real divided by 10, so the share of loss on every partner is only 100,000, as it is 10 times smaller as compared to before. So in such cases, and if you are going to do the same business again alone, again loss, big mushkila. No, not repeat. Repeat is some other meaning here. You should increase the number of oscillations so that the uncertainty percentage is reduced. That is the concept basically. Okay, so now answer 90, wait a minute. So it is 19.7 over 0.888 square. And I'm getting 24.98. So here answer is 24.98. And of course, we will never go for these four significant figures. We need to use less. It can be 25.0 more suitable if we are rounding it off. So 25.0, that is the answer. Newton meter is already written. Now method 2. The student measures the stretch length L of the spring with 500 gram mass still attached is in centimeters to the nearest point 1 centimeter. Figure shows the stretched spring drawn to a scale of 1/4 of full size. Okay. The length L of this distance between the dotted lines in the figure, measure L. Now I'm going to measure it, but of course I have zoomed in the I have zoomed in this measurement, so because we are in practice, so no problem. Or I will check in the mark scheme what is their answer. So for me, if I'm measuring, answer is coming almost 6.5. It is of course more, and anybody can open the mark scheme and let me know what is the answer. Okay, wait a minute. It is, sorry, 6.5 centimeters, but it is more. Okay, no problem. Let's go with this. Wait. Why I'm not convinced with this answer? Because this paper is zoomed in. The screen is zoomed in. So not the exact answer. Yes, it should be 5.6. So instead of this, I'm writing here how much? 5.6 centimeters. Calculate the actual stretch length of the spring. 5.6 times 4. 5.6 times 4. 22.4. Who will tell me why so? Reading the question carefully is the key to success. Come here. Figure shows the stretched spring drawn to a scale 1/4 of full size. It means here it is shown 4 times smaller. 1/4, 1/4 of the full size. So it means actually it will be 4 times larger. So that's what I did. 5.6 is the length between the dotted lines. What do we mean by dotted lines? From here till here, and we are never using this coil hook's length, only coil length. This was 5.6 centimeters. This is 4 times smaller than its actual size. So actual size will be 5.6 times 4. And record L in table 1.2. So it is 22.4. The student removes the 100 gram mass from the mass hanger at one at a time. So see 100 less 400, 400 minus 100, 300, 300 minus 100, 200 and then 100. And repeat the procedure. The student record each value of length in table 1.2. He has done it. Now of course they will go for the graph. So plot a graph of length in centimeters on y-axis against mass in grams on x-axis. Start your both axes. So it is already labeled. See one labeling mark they minus. Otherwise before always it is 4 marks. But in that case we are labeling. Right now labeling is done by them. Now mass is from 0, 100 to 500, and it means I can do, this is simple graph by the way, according it looks to me. This is 100, this is 200, 300, 400 and 500. More than half of the grid is covered with data on x-axis. Now y-axis, let's see the length that starts from 6 till 22. I can go like with 5. 5.0 here, 10.0, 15.0, 20.0, then 25.0 also. So why so? In this way also you have scored our first mark, because the data is scattered or more than half of the grid on y-axis as well as on x-axis. Now each box, small box on y-axis, length axis, it is representing 0.5 centimeters. With 2 boxes equal to 1 centimeter. On y-axis, like what is represented by one small square, that you can write 5.0 minus 0 divided by 10, 0.5 centimeters. So each 2 small boxes will be equal to 1. Now we need to plot these points accordingly. At 500 mass to 22.4, length is 22.4. 500 is over here. This is 20. This is 21, this is 22, this is 22.5. So very near here, like this. So that is 22.4, almost 22.5, because 2 small boxes on y-axis equal to 1 centimeter. Now 400 gram, 18.3, 400 gram, 18.3. See, this is 15, 16, 17, 18, this is 19, so this is 18, 18.5, so 18.3, very near here. Then at 300 the value is 14.3, 14.3. 300, see this is 15, 2 box, this is 14, this is 14.5, so 14.3 somewhere here. Though okay, then at 200 it is 10, 200 it is 10. Then at 100 I think 6.1, almost 6. This is 5, this is 6, almost 6. Now what we are going to do, now we have to draw the line of best fit here, line of best fit here. So line of best fit, I will try my best to draw it. So this is the line of best fit, not passing through origin. So we scored first mark by labeling, second mark by the crosses, and third mark by the graph line. And this thickness of the line should not be more than the thickness of these big square lines, major lines of the graph. Calculate the gradient G of the line. Show all your workings and indicate on the graph the values. Of course, I told you many times now, whenever we are going to plot, we are going to calculate the gradient, we need to show a triangle, lazim. So triangle shown on the graph, and it should be as large as possible triangle. Then of course this is x2, which is 500, x1 it is 0, y1 that is equal to see 1 2 3 4, so it is equal to 2 because one box is equal to 0.5 centimeter. And what about y2? So 20, 21, 22, 22.5. 22.5. 1, 2, 3, 4, 5 lines. So this is what, this is y2 here. The examiner told that your values must be shown. So now what is gradient? Write the formula, which is equal to y2 minus y1 rise over n over x2 minus x1. x2 is 500, x1 is 0, y2 we will see up, but y1 is 2, so y2 is 22.5. Let's check what is the value of gradient. So it comes to be 22.5 minus 2 over 500 minus 0, and the answer is 0.041. 0.041. 0.041. So write it here, 0.041. No need of the unit. Next is an estimated value K2 of the spring constant of the spring can be calculated using the equation K2 is equal to 1 over G, with reciprocal of the gradient. So K2, using your value of G from E2, gradient value. So value of K2 is equal to 1 over so 1 divided by 0.041, 24.39, 24.39. So 24.39, I'm not going to write this, I will be writing 24.4 Newton per meters. Yes, my dear friends, if any one of you is having any problem here, please feel free and you can ask me. Okay, now let's move forward. Lengthy question, and first time I'm seeing a question which is 13 marks. In general, maximum marks are 11. Okay, two quantities can be considered to be equal within the limit of experimental accuracy if their values are within 10% of each other. I told you already, we are following this 10% uncertainty. Compare your values of K1 from C and K2 from E3. State whether your results support the suggestion. I will say yes. Reason: because they are within the limit of experimental accuracy. You will say, sir, how do you know? Let me tell you here. So calculate percentage error, or you can write uncertainty. 2 times the difference of the values in the numerator, 25 minus 24.4 is what? 24.4, yes. And first value of k is 25 here. Yes, here somewhere. No, that is here. See, 25. So over 25 plus 24.4 times 100%. Let's calculate this value. (25 minus 24.4 over 25 plus 24.4 times 100. Answer comes to be 2.4. How much percent? It is only 2.4%. So of course this is less than 10%. 2.4 means your answer is 97.6% accurate. So high ratio of accuracy. So whenever, even if it is not mentioned in general for IGCSE point of view, it's better that if your percentage error is less than 10%, which means your answer is above 90% accurate, so write yes and then within the limit of experimental accuracy. If it was 24%, mean after calculation the answer was going to be 24%, I was going to write no, outside the limit of experimental accuracy. But if value of k1 is 25 and value of k2 was also going to be 25, I was again going to write yes, but no more within the limit of experimental accuracy. I was going to write yes and then they are equal. I'm sure this is very clear to you all. Let's move forward to question number 2, which is of course on electricity. A student investigates the resistance R of the diode using the circuit shown in figure 2.1. The student, and what is there? There is an emitter, diode, voltmeter cross the diode, X and Y between these points, 10 ohm resistance is connected, DC power supply because positive negative is there, and this is a switch. The student closes the switch, records the voltmeter reading V, records the ammeter reading I, opens the switch. Figure 2.2 shows the readings on the voltmeter and ammeter. Record the readings on the voltmeter and ammeter in the first row of the table 2.1. See 0.5, 0.6, 0.7, 0.8, this is 0.9. So this is 0.8, 0.82, 0.84 volts. Current 1. So 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.91. Okay. So this is 0.1, 0.2, 0.3, this is 0.4. So 0.32, 0.34, and this is 0.36 amperes. If anybody did not understand, can ask me. Okay, no problem. Let me say, see, 0.1 minus 0, this is 0.1, divided by 2. So 0.1 divided by 2, 0.1 divided by, not 2, divided by 5, sorry, 0.02. 5. Why 5? Because 1, 2, 3, 4, 5 divisions are there. So 0.02 volts. So see now, 0.5, 0.6, 0.7, 0.8, so 0.82, 0.84. Same is the case here. See, this is 0.1. So 0.1 divided by 5, again 0.02. So this is 0.3, so 0.32, 0.34, and this value 0.36. So like this, you can find the what is one small division. Here also, what is one small division? They are same because exactly the same scale is there. Only one is for voltmeter, other one is for ammeter. Okay, voltage reading is 0.84, 0.84, and current reading is 0.36. 0.1, 0.2, 0.3, yes, 0.36. Now, calculate the resistance R of the diode using your meter readings from A. R is equal to V over I. V over I. So 0.84 divided by 0.36. 2.33. So I can write simply 2.3. First row of the table to a significant figures, because this is one decimal place, so also this is one decimal place. Record your answer in the first row of the table like this. The student connect 3 ohm resistor in series with 10 ohm resistor like this, 10 and 3 now between the terminals X and Y, and the data is given in the table. Then he connects 7, 10 and 3 in series, and the data is there in the table. Complete the table. Table 2.1 is incomplete by adding the missing values of R and I. No problem at all. So missing value of R, it means 0.83 divided by 0.27. 0.83 divided by 0.27. 3.07. So I can write it 3.1. What is the value of current? I is equal to V over R. So for this, from Ohm's law, I is equal to V over R. So 0.81 divided by 4.5. So 0.81 divided by 4.5, it is 0.18. So table is completed and we scored further 2 marks. As the resistance between X and Y is increased, the current in the circuit changes. Use your results in the table 2.1 to state the relationship between current in the circuit and the potential difference V across the diode. Resistance is in the terminals changes, the currents in the circuit changes. Now we have to use the results in table 2.1 to state the relationship between the current in the circuit and potential difference. Current in the circuit and potential difference. Current in the circuit and potential difference. Now you can see current in the circuit decreases. Current before 0.36, then 0.27, then 0.18, but potential difference is almost same. This is one thing. Then, okay, let's write it. As the current in the diode, in the circuit, okay, current in the circuit decreases, potential difference, I'm writing P dot D, remains almost the same, because not a big difference, 0.84, 0.83, 0.81, this is almost same. Resistance of the diode. Now what happens to the resistance of the diode? Let's check. Current decreases and resistance increases. Here we can see current is of course decreasing, and what is happening to resistance? The resistance is increasing, in getting more. So as the current in the circuit decreases, the resistance increases. As the current in the circuit decreases, as the current in the circuit decreases, the resistance in the circuit increases. So just see the trend in the table and then write the answer. Please, any one of you having any question regarding this, feel free, you can ask me. Now, my dear friends, a student attempts to set up the circuit shown in figure 2.1. The student finds the ammeter does not give a reading when the circuit is complete. The ammeter is not broken, mean it's workable. Suggest what the student may have done incorrectly while setting up the circuit. While what? Setting up the circuit. Yes, please. My dear friends. Now we know there is a diode into the circuit. See, this is positive, this is also positive side of the diode, negative, so diode conducts current flows. Everything may be fine, either he have reversed the battery or he have reversed the diode. Mean there is a possibility maybe he made this side negative and this positive like connected this way, and then ammeter is there, and now in this case diode will not work, or battery is same way, positive negative, ammeter on its place, but he has reversed the diode. In this way also it will not work. So what are the possibilities? Why ammeter is not giving the results even everything is correct? So you can say student may have flipped the power supply or diode. You can write only one of them. Student may have flipped the power supply or student may have flipped the diode. Name a single device that can be used to control the current in the circuit instead of adding extra 3 resistors in series. Draw the circuit electrical symbol for the device. This is very common, very common. See, name of the device, that is variable resistor. Symbol, very simple, this way. So in this way, this question number 10 is also done. Question number 2 is also done. Anybody having any problem, any question or query here, feel free. You can ask me now. Yeah, let's start this light question, refraction of light. A student investigates the deviation of a ray of light, means change in direction of the ray of light through a transparent block ABCD, and measures a quantity called the refractive index N of the block. Refractive index N of the block. The student's ray trace sheet is shown full size in figure. Okay. On figure, draw a normal at point E, extend the normal above AB and below CD. Above AB and below CD, no problem. Just first of all, we need to draw the normal, which means a line at 90 degree to E. Like this. Okay. Label the upper end of the normal with the letter N and the lower end of the letter M, and the point with normal CD with letter G. So N, M and G. This is N. This is M, and this point will be labeled as G. Don't forget to label them with the alphabets told by the examiner. 1 mark. Measure the angle theta between the lines FE and EN. Right now I don't have the protractor, so roughly I will measure. It looks to be bigger angle by the way. maybe 60, maybe 65, like this. Okay, let me write it 60. No worries. 60 degrees. But again, how will you put the protractor? My dear friends, always remember, put the protractor such that the baseline of the protractor is on the normal, center of the protractor here. This is the center of protractor when you are placing center of protractor, and here 0 and 180. You will start from 0, 0. This will be 60 degrees. Okay, so I'm writing here angle is equal to how much? 60 degree between the line FE and EN. Then, now, the student positions an illuminated slit on the ray trace sheet, like even you can say laser, illuminated slit at the ray sheet, not laser, sorry, so that the ray of light passes along the line FE towards E. Mark and label with small crosses X, marks with and labels with X the two pins on the ray, leaves the side CD of the block, removes the transparent block. On figure 3.1, extend the line FE until it meets the right angle edge of the ray trace sheet FE. Label the end of this line C. Extend the line FE until it meets the right hand edge of the ray trace, right hand edge of the ray trace sheet FE. FE, this one. We will stretch it till it touches the right hand edge, and we label that point. Okay, and we have to label it with the letter Z. Z. Then nothing from our side. We are just following the instructions of the examiner. Draw a line, straight line through the two crosses to meet the side CD of the block. Label the point where the line meets CD with letter H. Label the other end of the line with the letter J. Draw a straight line from E to H. Okay, first of all, letter H, where see these crosses. Here he said label it H, other end label as J, and then a straight line from E to H. Just the instructions of the examiner I am following. Nothing from my side, no perception. This way. Now let's see. He said to use letter H where it meets CD and other end with J and join E to H. Measure the length L of EH. So measure the length L of EH. I'm measuring it. So, and please use the centimeter side. 7.7 for me. How much? I'm writing it 7.7 centimeters. Then measure the perpendicular distance D between the line HJ and FZ. HJ and FZ. HJ and FZ. Perpendicular distance between HJ and FZ. So perpendicular distance, my dear friends, will be like sorry. Perpendicular distance. This is D, by the way. Straight line but perpendicular distance such that this angle should be 90 degree. So when I am measuring this with the ruler from here till here, I am getting it almost, and be careful, you have to use the centimeter side. It is almost for me 3.1. Now calculate d over L. D over L. So 7.7 over 3.1 centimeters, centimeters cancelled. So my dear friends, 7.7 divided by 3.1, it's equal to 2.48. So I can write 2.5. So it is coming to be 2.48. Let it be 2.5 and there will be no unit. Even 2.48 will be workable. Oops, nobody is telling me, sir, you are doing wrong. It is D over L. So 3.1 over 7.7. 3.1 divided by 7.7. So it is 0.402. So just 0.40. So 0.40 without any unit. The measurements of a quantity is reproducible if similar result is obtained when the measurement is repeated by a different method or under different conditions. Suggest that how the student can adopt this experiment to check if the D over L is reproducible. Okay, there is one response. Yeah, 0. Shija, okay. Reproducible. So he has done this experiment with the light. So repeat the experiment with optical pins. Before we are doing like this, not using light, optical pins, or even he can do repeat the experiment with angle of incidence is equal to 60 degree to the other side of the normal to check that it is workable or not. Right now it was left side of the normal. Now he can do it with the right side of the other side of the normal. Okay, suggest one source of inaccuracy in this experiment if it is carried out very carefully. Light ray thickness, you should use a thin source of light. You can say thickness of the light ray. It should be thin source of light. These are some common points. Now measure the length L of GH. L over GH. L of GH. Okay. For me, when I'm measuring again, I'm saying it should be in centimeters. And when I'm placing it, so it is, for me it is, again, 4.5. Because it is zoomed in screen. For you, of course, if you have printed this paper, it will be less. So 4.5 centimeters. Use your values of L from CI and L from this to calculate the value N for the refractive index of the block. Use the equation which is 0.866 times over 4.5. What is L from CI? 7.7. Here 7.7. So 7.7 divided by 4.5 equal to this times 0.866, 1.48. 1.48, even you can write 1.5 even. That will be workable. No worries. So 1.5 even, that will work. Now, my dear friends, still one question is left, that is planning question, and this question will be your homework. If you will be doing it well, nice. If you will not be doing it well, inshallah, the next session we will be discussing. So, this is your homework from 22 to 2025. Okay, my dear friends, any question you can ask me. Stay blessed to all of you and have nice vacations.